Hello friends, I welcome you in lecture number 7 on complex differentiation. From last several lectures, we are discussing different types of problems on determining the differentiability of a complex function. And you might have noticed that in every problem we have different curves in which Cauchy-Riemann equations are satisfied. In this lecture also we are going to discuss two more problems on determining the points at which given function is differentiable. So here I am going to consider this function and I will check that at which points in the complex plane this function is differentiable, and you can see here right hand side is already in this form u plus iv. In earlier problems, we are not given our function directly in this form. Therefore, we have converted by taking z equal to x plus iy in the formula of a given function. But here we are already given our f of z in this form. So, we have our real and imaginary parts which we denote by u and v respectively. This I can compare as, suppose this is equal to u plus iv, then if we compare x square plus iy square with u plus iv, it is clear that u is x square and v is y square. Then as usual we have to first determine the first order partial derivatives of u and v with respect to x and y. Here first we differentiate u with respect to x, and derivative of x square with respect to x is 2x. Then for del u by del y we consider y as constant, we consider x as constant for differentiation with respect to y partially. So here x is constant, therefore x square is constant and there is no y term here. Therefore, derivative of u with respect to y is 0. Same thing here, while differentiating v with respect to x, we treat y as constant, therefore y square is constant, therefore del v by del x is 0. And del v by del y is derivative of y square with respect to y is 2y. Then in the next step, we determine the points at which Cauchy-Riemann equations are satisfied. So first we find out that when these two are equal, del u by del x and del v by del y are equal, if their right hand sides are equal, here right hand side is 2x, here it is 2y, and this we can rewrite as if x equal to y or y equal to x. What is meaning of this? These two functions are equal at all those points z for which x and y are equal, that is at this type of points 1 1, 2 2, -3 -3. So the points for which x and y components are same, or for those complex numbers in which real and imaginary parts are same, this equation is satisfied. Or we can visualize geometrically also. Y equal to x represents the straight line passing through origin and with angle 45 degree. With positive x-axis, angle is 45 degree. So suppose this line represents y equal to x, then this equation is satisfied at all the points on this line. The points on this line will look like this, z equal to ordered pair x comma x. So from this we have the idea that y equal to x represents this line in the complex plane. So this equation is satisfied at all the points on this line. Then for second equation we determine the points for second equation. Del u by del y is 0 and del v by del x is 0, therefore minus del v by del x is also 0. So this equation is satisfied at all points because right hand side is 0 for both the functions. del u by del y is 0 and minus del v by del x is 0. Both the functions are 0 at all points. That means both the functions are equal at all points, and that means this equation is satisfied at all points z in the complex plane. And first equation is satisfied at points on the line y equal to x. Second equation is satisfied everywhere on the line as well as everywhere in the complex plane. And we are interested in those points at which both equations are satisfied. So first equation is satisfied at all points on the line. Second equation is satisfied at all points in the plane. Therefore, the points which are common are the points on the line y equal to x. We can say that both equations are satisfied at all the points on the line y equal to x. And the points which are not on the line, both equations are not satisfied, because this equation is not satisfied at those points which are not on the line. Therefore, we can write that both Cauchy-Riemann equations are satisfied at all points on the line. At all points on the line y equal to x only. This means here equations are not satisfied at those points which are not on the line y equal to x, and that means function is not differentiable at a point z if z is not on this line. If z is somewhere here, then z is not on the line, and Cauchy-Riemann equations are not satisfied at those z which are not on the line. Therefore, we can say that function is not differentiable at those points which are not on the line y equal to x. So that also we can write that first we are writing that therefore f of z is not differentiable at those points which are not on the line, is not differentiable at those points which are not on the line y equal to x. And for the points on the line y equal to x, this is not enough. We have to check another condition also for differentiability. One condition for differentiability is satisfaction of Cauchy-Riemann equations, and another condition is continuity of first order partial derivatives at those points. So we can see that these functions are polynomials and constant functions, and we know that polynomial functions or constant functions are continuous at every point in the complex plane. Therefore, all these first order partial derivatives are continuous at all points on the line y equal to x also. So that we have to just mention, but we should check. There are some functions for which Cauchy-Riemann equations are satisfied, but they are not differentiable because this condition is not satisfied. So clearly these first order partial derivatives del u by del x, del u by del y, del v by del x, del v by del y are continuous at all points on the line y equal to x. They are continuous everywhere, but here we require continuity at points on the line y equal to x. So we can say that Cauchy-Riemann equations are satisfied at all points on the line y equal to x, and all these functions are continuous at all points on the line y equal to x. Therefore, we can say that function is differentiable, f of z is differentiable at all points on the line y equal to x only, because it is not differentiable outside the line. So I am using the word at all points on the line y equal to x, or we can say that f of z is differentiable at a point z which looks like this. At point z equal to order pair x only. And what is derivative? And f dash z is given by del u by del x plus I times del v by del x, but our function is differentiable at this type of points only. So we have to find out del u by del x at point xx plus I into del v by del x at point xx. Before that, we write down what is del u by del x. It is 2x, and del v by del x is 0. So this is 2x plus I into 0. So del u by del x at xx, this is at arbitrary point z. So here also it is 2x, and here also it is 0. So this means we obtain derivative equal to 2x. So we can say that f dash z equal to 2x, and here z is this type of point because function is differentiable at these points only. And you should be clear about this. Here when I am writing del u by del x equal to 2x, that means at any point xy it is 2x. So whenever I consider ordered pair x comma x, then also it will be 2x because x is used only here. Same thing, del v by del x at any point xy is 0. Therefore del v by del x at point xx is also 0. So I have written this here, and I am able to decide the differentiability of given function, and I find that given function is differentiable at all the points on the line y equal to x only, and if we consider any point on that line, then derivative is equal to 2x. For example, if I am interested at the point 2 comma 2, then here derivative is given by 2 into x coordinate, that is 4. Similarly, suppose I want to write down derivative at point 3 3, then it is 2 into x component, which is 3, which is 6. So in that way, this is the meaning of derivative of this function. So this is very interesting example. Here function is differentiable at infinite number of points, but those infinite number of points are those points which are on the line y equal to x only. And remember this example, we will require this in upcoming lectures also. Now we see another function and we check its differentiability. Here we are already given that show that function has no derivative, and if f of z is 2x plus ixy square. So we have to prove that this function is not differentiable at any point z in the complex plane. So it is also given in the form u plus iv. So first we write down u and v by comparing this right hand side with u plus iv. So if we compare, we find that u is 2x and v equal to x into y square. Then we find out partial derivatives. Therefore del u by del x is derivative of 2x with respect to x is 2. Del u by del y is derivative of 2x with respect to y, which is 0. Here del v by del x is derivative of xy square with respect to x, and we consider y square as constant. Derivative of x is 1. Del v by del y is x is constant, derivative of y square is 2y, and we have 2xy. Now we find out the points at which CR equations are satisfied. So first we check at which points these two are equal. Del u by del x equal to del v by del y if del u by del x is 2 equal to del v by del y is 2xy, and this I can rewrite as x into y equal to 1. So this equation is satisfied at all those points which satisfy this condition, x into y equal to 1. That means if I consider 2 comma 1 by 2, say z equal to 2 comma 1 by 2, then product of 2 and 1 by 2 is 1. Therefore this equation is satisfied at this point. Similarly I can write 1 by 3 comma 3. So we have to find out the equation, or we have to understand that which curve is represented by this equation, x into y equal to 1. So if you recall, this x into y equal to 1 is nothing but rectangular hyperbola in first and third quadrant. It will look like this. Okay, it is a rectangular hyperbola and it will never cross x axis and y axis. It will go parallel to x axis in this direction and go parallel to y axis in this direction. Similarly we have this type of graph. It is symmetric in opposite quadrants, that is first and third quadrant. If I consider this, I can rewrite this as y equal to 1 by x. So this means x is approaching 0. If x is going in this direction, then you can see y will be 1 by 0, that is y will approach to infinity. So if we are decreasing x, that is if x is approaching 0, y will increase in this way. Same thing for this part also. We are interested in visualizing that in which part of the complex plane this equation is satisfied. So this equation is satisfied at all those points which are on these two curves. These two curves represents this rectangular hyperbola, or we can say that this is single curve having two branches in first and third quadrant. Now we check that at which points second equation is satisfied. We know that second Cauchy-Riemann equation is del u by del y equal to minus del v by del x. Del u by del y is 0 equal to del v by del x is y square. So minus del v by del x is minus y square. So this means if y square equal to 0, that is if y equal to 0. This means this equation is satisfied at all those points z equal to xy for which y component is 0, and we know that all these points are on x axis, and if you recall, this y equal to 0 is the equation of x axis. So this equation is satisfied at all points on x axis. Uy equal to minus vx is satisfied at all points on x axis, and ux equal to vy is satisfied at all points on the rectangular hyperbola x into y equal to 1. And we are interested in those points at which both equations are satisfied. So you can see from this figure that there is no common point at which both equations are satisfied. So we can write that there is no common point at which both equations are satisfied, or we can say that both Cauchy-Riemann equations are not satisfied at any point, are not satisfied at any point in the complex plane. So that means function has no derivative at any point, or f dash z does not exist at any point. In other words, function is not differentiable at any point, or we can write that f of z is nowhere differentiable. F of z is nowhere differentiable. Now suppose you don't want to sketch this figure, then also it is fine. It is not necessary to sketch the figure. This is just to understand the geometry, that how we can find out the common points. Now suppose you don't want to sketch the figure, then also you can decide from the equation of curves. We know that this equation is satisfied at all those points for which x into y equal to 1, and this equation is satisfied for y equal to 0. Now if I put y equal to 0 in this equation, then left hand side will be 0 and I will get 0 equal to 1, and that is not possible. So from this also we can say that these two equations are not satisfied at any point. If I put y equal to 0, then this equation is not satisfied. So from this also you can decide that there is no common point at which both equations are satisfied. So in this way we can check the differentiability of a complex function using Cauchy-Riemann equations. But be careful, this is not only requirement, we have second requirement also, that the points at which CR equations are satisfied, we have to check the continuity of these first order partial derivatives also, and if these two conditions are satisfied at any point z, then function is differentiable at that point z. So this is all about this session. I hope you like it. If you have any doubts, you can ask in comment section. Thanks for watching.